Okay, let's continue to talk about the suitable magnetic materials. As shown in the image, magnetic nanoparticle as a carrier for MRI enhance the original weak MRI signal, play a role of amplifying the MRI signal, and improve the pulse sensitivity of MRI as a molecular imaging device. Therefore, it's very important to choose which materials to use as the carrier of MRI. The contrast agent currently used in MRI molecular imaging can be broadly divided into two classifications. Let's talk about them one by one. The first is the paramagnetic. This is mainly composed of ions of the transition elements of the lanthanide metals, which are combined with chelators by chemical bond to form stable chelate. We usually use the non-technical contrast agent in clinic are gadolinium DTP and gadolinium DOTA. Taking gadolinium ion used in the clinical practice as an example, the reason why it can become a good paramagnetic substance is that there are 7 unpaired electrons around gadolinium ion, which can produce positive signal of T1. Therefore, this contrast agent can be used to purpose targeted molecular probe to achieve MRI molecular imaging. However, gadolinium chelate has a certain degree of cytotoxicity. For example, as we know, the renal system fibrosis, NSF, which has become one of the shortcomings of its clinical application. In addition, the particle size, specificity, and the imaging concentration of small molecular contrast agents are also equal in clinical application. In terms of the MRI molecular imaging, gadolinium or its chelate are usually connected to the surface of the carrier, and the active or passive targeting characteristics of the carrier probe are used to achieve the specific imaging of the target area. The advantage of the nanomaterials are high imaging efficiency and a wide application range. The disadvantages are free toxicity of the gadolinium ion and the relatively large molecular probe. So in the image, for example, there is the gadolinium nanorod with C on the left and T on the right. According to the ruler, its particle size is about 100 nanometers. To apply the material to MRI, we need to measure the imaging effects of the material, namely its relaxation rates. The slope of the oblique line in the Brookline diagram shown is the gadolinium relaxation rate. The right shows the T1 imaging effects of the different concentration of the materials and control group PBS. And we can see there is a good gradient effect. For another paramagnetic material, this is magnesium. Its advantage for MRI is that it has 5 unpaired electrons and a long relaxation time. It also natural component of cells, usually as a cofactor of the enzymes and the receptors, and has the characteristics of the low toxicity and high specificity. But at the same time, nerve and liver toxicity is also one of the disadvantages of the magnetism as a nanomaterial. At present, the specific metabolic mechanisms and long-term toxicities of this enzyme still need to be further studied. Here, we present an image. We can find the image materials and PET modification. These two images are fine studied by Shea and his colleague. The nanomaterial is characterized by its unique features in weakly acidated microenvironments of the tumor tissue, which can significantly improve the in vivo or in vitro performance of the T1 weighted image. This pH tracked split may also facilitate the rapid release of loaded anti-cancer drugs of the diagnosis and treatment of the concurrent pH-reactive cancer. So we are continuing to talk about another materials. This is super paramagnetic materials represented by iron oxide. Currently, SPL particles are about 50 nanometers. However, ultra-small paramagnetic iron oxide particles, USPL, are less than 5 nanometers, which are commonly used. The main characteristics of these materials are small particle size, stronger permeability, and higher relaxation rates. From the perspective of the biological application, the greatest advantage of such materials is their biodegradability. After being metabolized by cells, the materials can enter into the normal plasma ion pool, which is of high safety. The result of the laboratory study also showed that the cell labeled with super paramagnetic substance after transfections don't have short-term and long-term toxic and side effects, and they are a kind of safe, effective, and highly specific molecular probe. So they are widely used in the MRI molecular imaging. SPL are shown in the image. According to the image, we find the particle size is about less than 15 nanometers. Okay, this is all for this part. Thank you.